Okay, with this lesson we get into what I consider the very heart of the Calc 1 course. We're going to use all the theorems that we've just learned over the last couple of lessons and apply them to graphing functions. And it's more than just graphing them. It's basically understanding what a function function acts like. And of course the way you can best do that is to graph it. So let's go ahead and take this one. I'm going to go through all the steps that I normally go through with any function that I want to do this with. So the first thing I do whenever I see a function like this is I ask, what's the domain? What are all the values that you can stick into it? In this case, there's only kind of three restrictions. One is, of course, you can't divide by 0. You can't take the square root or the even root of negative numbers. And then the other one is the ln. The ln has a domain of just positive numbers. So those are the three things you need to watch for. And this one has none of those. So the domain in this case is everything from minus infinity to infinity. The next thing I ask are, what are the intercepts? Okay, of course there might not be intercepts, but generally there may be. So the y-intercept is what happens when the x value is 0. So since you can stick a 0 into this function, notice that put a 0 in and a 0 out, and you have the x-intercept. Okay? Oh, I'm sorry, that's the y-intercept. That's the y-intercept. And I say the y-intercept because there can only be one y-intercept, right? On the other hand, there can be lots of x-intercepts, right? You can have a function go through at 0, but it can go through other places as well. So to find out all the x-intercepts, you say, where will the function be 0? So in this case, we go 2x cubed minus 6x squared. Set that equal to 0. I can factor a 2x squared out of both terms, and I'm left with x minus 3 is equal to 0. And now I see that this thing is equal to 0 at 0 and at 3. So those are the intercepts right there. I guess I can write them down. Okay. But we want more than that. Those are the two places where the function is 0. Everywhere else, it must be either positive or negative. So let's determine which. So this is the easiest form of the function right here, since everything is factored. Let's go ahead and just put in a value larger than 3 here and see whether the function is positive or negative when we do. So let's put in a 4. If you put a 4 into this, it's going to be positive here. 4 minus 3 is positive. Positive times positive is positive. So I make the claim just by throwing 4 in that this is going to be positive all the way through there. Why can I make that claim? I'm basically using the intermediate value theorem, because I'm saying that here's this, by the way, this is notice it's a continuous function. It's differentiable everywhere. The derivative exists everywhere, and that means it's continuous everywhere. And since it's continuous everywhere, and it's 0 only at these two spots, then if it happens to be positive anywhere beyond 3, then it's got to be positive everywhere beyond 3. Why? Because otherwise it can't break and suddenly jump from here to here. That would be discontinuous. If it goes on through like this, which any continuous function would have to, then you'd have another intercept farther on, but we don't. The only intercepts are 3 and 0. So this is a key place where we're using the intermediate value theorem without even really thinking about it. But it all comes from the fact that the function is continuous. Once it goes into positive territory, there's no way for it to come back unless we know about it, which we don't. Those are the only two places where it's 0. Any place where it comes back, it's got to cross the x-axis again. And there's no place where it's crossing the x-axis, so it's got to stay positive. So it's positive there. Stick in a value convenient in here. How about a 1? Put in a 1 here. It's going to be positive. This is going to be negative. So it's going to be negative throughout. stick in a -1, for example, and you're going to get -1 squared is positive, so this is positive, and negative, so it's going to be negative there. Okay? By the way, it's easy for me to see when it changes sign. It changed sign at 3 because at 3 you're switching from one side of this to the other. And the line x minus 3 looks like this. It goes through there. It's positive on one side and negative on the other. So this line right here crosses from positive to negative at 3. On the other hand, x squared, what does that function look like? As you go from one side of 0 to another, which is what's happening here, notice it's positive here and positive there. So at x squared, it did not change sign, but at 3 it did. So basically, it depends on the power. When you multiply them all together, these even powers, the function's going to look roughly like this. Odd powers, it's going to, if you think of what x cubed looked like, it cuts through. There, it's going to change sign. So anyway, that's a good test. Okay, so we know that. That's all important stuff to know. So now we not only know the intercepts, but we know this. Next thing. This is something we haven't talked about for a while, but wrote asymptotes, but I mean symmetry. Let's check to see whether this function is even or odd. Remember what it means to be even? It means that whatever it does here does exactly the same thing there. Odd means if it does this, then it does the opposite as you go down the other side. So remember how to do it? Here's what we do. We take a negative x, put it in for x, and so we're going to get 2 times negative x quantity cubed minus 6 times negative x squared. And when you pull the negative times negative times negative, you're going to end up with a negative 2x cubed. This is just going to go away, minus 6x squared. I look at this and I say, oh, it's not the same as my original function. If it were exactly the same, I would have an even function. Nor is it the negative of the original function. I could factor a negative out of here, but if I do, I'm now left with 2x cubed plus 6x squared. So if I try to write it as a negative, nope, I have a different function than I began with as well. So it's neither even nor odd, no symmetries at all. So we can say none. Okay. Then asymptotes. Asymptotes, basically we're asking what happens. Are there any places where the function blows up like this? Perhaps, maybe does something like that. Or those are vertical asymptotes. Those are places where along a vertical line it gets closer and closer as we go. Or horizontal asymptotes. Horizontal might be something like this. Something like that, where it gets closer and closer to whatever this line is. Y equals, what does that look like? 2.7? Maybe 2.7. So do we have either? Well, first of all, we don't have any vertical asymptotes because in order to, recall, we'd either have to have one of those ln's or we would need to have a denominator that goes to 0. And there's none of it here. So there's no vertical. Okay. For horizontal, this basically is asking the question, what happens as x goes off to infinity? So let's just write that down. What's the limit as x goes to infinity of the quantity 2x cubed minus 6x squared? Okay, so let's look at that. This is going to get big. This is going to get big. If you subtract one big number from another number, it's not really clear what's going to happen. If you remember some of the things we talked about, this is going to get big faster than this. So it might well seem that this is going to dominate things. Let's see once if we can just justify that. Let's factor a 2x squared out of both of these things. We're left with x minus 3. Everyone agreed? So we get this. Now it's clear. As x gets big, this is going off to infinity. X is going to obviously be bigger than 3 right away, so that's going to go off to infinity. You take two big numbers and multiply them together, and the thing's going off to infinity. So there's no horizontal asymptote. It's not going to level off, but this is kind of important to know as well. So let's just write no horizontal, and we'll also write this little bit of information that the limit of f of x as x goes to infinity is equal to infinity. And we might as well do minus infinity at the same time. As x gets to be a big negative number, then what happens? This is still going to be positive. This is now going to be a negative number minus 3, which is going to be negative. What happens when you multiply a big negative number by a big positive number? It's going to be a big number, and the sign will be negative. So that's kind of important to know as well. And for lack of room here, I'm just going to say x goes to minus infinity. The answer is minus infinity. Okay? So we've gained a lot of information about this function, and notice we haven't used any calculus yet. Okay, this is all the stuff that you typically learn in a pre-calculus course. Although you might not use the word limit, you at least have that idea down. Okay, now we're going to ask the question, where is this function increasing and where is it decreasing? Okay, this is where we need derivatives, because as we just learned in the last lesson, it's increasing wherever the derivative is positive. It's increasing there, and it's decreasing when the derivative is negative. So let's go ahead, take the derivative. It's easy enough. We're going to get 6x squared minus 12x. There's the derivative. We want to know where that's going to be 0. So I'll factor a 6x out of both of them, and I'm left with x minus 2 is equal to 0. And we'll do the same thing we did here. We'll ask, where is the derivative positive and negative? Notice that it's going to be 0, both at 0 and at 2. And if you stick in a number greater than 2, both of these things are positive. So the product is positive. If you put in a 1, positive and negative gives you a negative. Put in a negative 1, it's going to be negative, and negative is positive again. So keep track of the fact this is the derivative we're talking about. So if the derivative is positive, that means the function is increasing. If the derivative is negative, that means you're decreasing. If the derivative is positive, you're increasing again. Okay, so a lot of good information there. Finally, we want to know whether it's about the concavity. And the concavity, recall, we need to know the second derivative. So f double prime of x is equal to, what? 12x minus 12. Set that equal to 0. And you're going to factor the 12 out, and you're left with x minus 1 is equal to 0. So there's just going to be one spot where it's 0. For everything greater than 1, it's positive. For everything less than 1, it's negative. Be careful again, just keep track of what you're doing. This is the second derivative. So when the second derivative is negative, the function is concave down. When the function is positive, when the second derivative is positive, it's concave up. So these are a lot of fun to do, because now you have all this information, and now we have to put it all together and see if we can come up with a graph that agrees with all this information. And what's kind of neat is that sometimes you make a mistake in here and you come up with information which is inconsistent. There's no way you can get a graph that satisfies everything. If you have a function that's up here and you say it's concave down, but there's no intercepts here, well, you're stuck, because if it's concave down, doggone it, you're going to have an intercept eventually. Sometimes you have to go back and find out what you did wrong. Other times you just have to be more thoughtful and realize how you can go about graphing what it tells you the graph actually looks like. So I think I have enough room here. Let's see what we have. I've got a little more interesting things on the right-hand side than the left. So let me change it to look a little bit more like this. So here's the x-axis, here's the y-axis. I'm going to have to cheat on the actual values of the x here in order to get everything in. So what do? First of all, you have an intercept at 0, 0. So I like to label these points. Have another intercept at 3. Okay, 1, 2, 3 right there. So put a little thing right there. Okay, you got all that information. No symmetries, no asymptotes. Keep this in mind as we go. Okay, so how about increasing and decreasing? It increases until it gets to 0. So here's what I like to do. Until it gets to 0, it's both increasing and concave down. What does that mean? It's increasing and concave down until it gets to 0. So it must look something like that. You agree? Concave down, and it's increasing. Once you pass 0, it starts decreasing. Here's 2 right here. It decreases until you get to 2. And notice that it stays concave down until you get to 1. So there it stays concave down. Now once you pass 1, it starts becoming concave up. Like that. Remember what this is called? That's an inflection point. Okay, that's an inflection point right there. That's at 1. And what happens at 2? After you get past 2, it starts increasing, and apparently it increases, and notice it's going to be concave up, and it's going to go through this point right here, and keep rising up like that. And so that's the idea. This right here at 2 is called a relative minimum. Why is that? Because it's a minimum relative to its neighbors. Compared to its neighbors, put a little interval around there, it's the smallest value. This is a relative maximum, obviously, because around a little interval there, it's the largest. Functions can also have absolute maximums and minimums. If you have a function that looks like this, that would be an absolute maximum. That's the largest it takes on the whole domain. And similarly, you can have absolute minimums, or global. In other words, is a global max or a global minimum. Okay. So this is a relative min, relative max. So that's what the function looks like. That's what we're after. And we've got the concavity. We've got basically the general shape. We kind of know what this thing is like. So that kind of satisfies what you normally want to do when you graph a function. The only other thing I want to do with this one, just to illustrate a couple of the theorems that we had in the last lesson, is let's just assume, now that I have everything here, I'm going to get rid of some of this stuff, all the concavity material, just to give me a little more room. Get rid of this. Okay, in fact, I have all this stuff. So excuse me. So suppose we were interested in this function not on the whole domain here, but just on the interval from -1 to 4. Just from -1 to 4. That was our only interest. Okay, on that particular interval right there. Okay. I guess it really doesn't matter whether you call that the domain or not. In fact, I prefer going back to what we had before. The domain is still this, but now we are interested in it just on this interval. Okay, that's where our interest is. So on that interval there, first of all, what's the maximum and what's the minimum value of the function on that interval? Recall what we learned from the last lesson, or 2 lessons ago, I guess it was. We said that the max and the min either have to occur at one of the endpoints or at a critical point. And a critical point is either a place where the derivative is 0 or a place where the derivative doesn't exist. Okay? So here, if you didn't want to graph the whole function, but just wanted the max and min, so I'm just going to say find max and min on this interval. I guess I'm thinking about this as I read it. On the interval -1 to 4, then the places you'd have to check would be you'd have to stick in f of -1, f of 4, and then all your critical points. So in this case, you'd have to put in 1 and 2 as well. F of 1 and f of 2. And whichever the largest of those is, that's going to be the max. Whichever the smallest of those is, that's going to be the min. So, let's check them all out. Stick in a -1, you're going to get -2 minus 6 is -8. Put in a 4, you're going to get to what? 64 times 2 is 128. 4 squared is 16 times 6 is 96. Subtract the 2, you're going to get positive 32. Is that right? Positive 32. Okay, stick in a 1. You're going to get 2 minus 6 is -4. That looks about right. And put in a 2, and you're going to get what? 16 minus 24. -8. So this is kind of good anyway, because it's kind of nice to know where these relative mins and maxes are. We know that this one is at 0, 0. Now we know that this one here is at 2, -8. That's kind of nice to know. And at 4, we said the value of the function is what? Is 32. And this is the value, what? -1, -8, right there. Okay, so the largest value of the function on this interval is obviously right there, and the smallest value occurs at I guess the smallest value occurs in 2 places. It occurs both at -1 and also at 2. So if I drew this a little bit better, it would have come down maybe a little bit faster, so that that value there looks like it's the same as this value. So the negative value, the minimum value, occurs in 2 different places. See that? So there you have all the information you need. Now, the last thing I want to do on this particular function, just to illustrate the mean value theorem, is to, I guess I have all the information I need there, is to ask this question. If I were to take the average slope of this function from there to there, that's going to be f of 4 minus f of -1 all over 4 minus a -1. That's the slope of this line, agreed? So that's going to be 32 minus a -8 all over 4 minus a -1 is 5. So that's 40 over 5, which is 8. So in other words, the average slope from here to here of this function, the average derivative or average slope of the function is 8. Write that a little bit bigger. Okay, there's the average slope. How often and at what values does that average slope happen? Well, I can kind of see it again just by looking at my function here. It's differentiable all the way through. It looks like there's going to be one spot, maybe right about here, where that average slope occurs, and another spot, I don't know, it's kind of hard to tell. I don't know how exactly true my graph is, but maybe somewhere a little bit bigger than 2 it looks like. It's going to be right about there is where that slope is the same as this. Those are the 2 places where it occurs. Let's see if we can actually find it out. Where do they occur? So what do? I take the derivative, which, whoops, I guess I did. Oh, here it is right here. Here's the derivative. And I take the derivative, and I want to know where will the derivative be equal to this average value. So I'm going to Guess I can get rid of this stuff now. It'd be nice if I had several of these boards here. Okay, so in this case, I'm going to take the derivative and set it equal to this average value of 8. And so what values of x make that true? I can divide everything through by 2 and get 3x squared minus 6x is equal to 4. Makes it look a little nicer. I can bring the 4 over. 3x squared minus 6x minus 4 is equal to 0. Why do you want to set things equal to 0? Because recall, if you have the product of anything equal to 0, you know one of those two things has to be 0. 0 is your friend. Okay? So, can I factor this? I don't see how to factor just by looking at it, so I'm going to have to use a quadratic formula. So again, I'll need a little more space. Quadratic formula says you do what? X is equal to the negative of this is going to be 6. Here's the quadratic formula. If you have ax squared plus bx plus c is equal to 0, the x's which make that true are x is equal to minus b plus or minus, oops, I'm going to run out of room, b squared minus 4ac all over 2a. Okay? That's part of the algebra that hopefully you brought into this course. And so it's going to be 6 plus or minus the square root of negative 6 squared is going to be 36 minus 4 times a negative 4 is going to be positive 16 is going to be plus 48 all over 2 times 3 is 6, which is going to be what? 6 plus or minus, that's 70, 80, 84 all over 6, which is, oops, square root of that. And I can factor a 4 out and get 6 plus or minus 2 times the square root of 21 over 6. Factor a 2 out of both the top and the bottom, and you're going to get 3 plus or minus the square root of 21 all over 3. So if you figure those out, what are they going to be roughly? Hard to say. 3 over 3 is 1, so it's going to be 1 plus a little something. So here's 1. If you add the rest of it in, I think it's probably end up over there a little bit. If you take the 3 minus this and divide it by 3, you're going to be there someplace. Let you figure that out on your own. You can find out the decimal equivalence there. Okay, actually, I'm kind of curious. Got my trusty Hewlett-Packard here. So I'm going to go 21 square root 3 plus 3 divide. And it ends up being 2.52. So this value right there is about 2.52. That's where the slope is the same. And the other one is going to be 3 enter, square root of 3 there, subtract, 3 negative, roughly negative a half. So negative 0.52, roughly. So there they are. So we were on the right track there. Okay, this is an HP. That's a wonderful little calculator, 10C. Okay, very good. So in the next few lessons, we're going to do several more of these. We're going to do some involving logs and some involving exponentials and some with fractional exponents, all sorts of things. Each one, well, 4 or 5 of them, and each one will have unique features of it that you'll learn some neat stuff about graphing functions. Okay, so that's it.